Okay, so let's have a look at some exam questions. So some of these are fairly typical, some of these are probably A and A star. So this is going to take you a little bit of time, maybe 15-20 minutes, possibly longer. Pause the video and then have a look at the answers when you're ready. Okay, so question 1, so it's a Young's fringes experiment, so we're just looking at a double slit rather than diffraction grating. We would assume that the light sources are coherent, but it does tell us that, so that's useful. In this case, it's given us the wavelength already. Lambda is 6.4 10 to the minus 7. And it produces a fringe pattern, which is what we'd expect. We're told the slit separation, 0.12 millimeters, so watch out for the millimeters. We'd have to convert that into meters. And the distance between the slit and the screen is 1.5 meters. So part A, really typical question, find the fringe separation. Okay, so we have our formula up here. The fringe separation is y, or delta y. So we need to make that the subject. So y is equal to lambda d over a. So we just substitute the values. So we've got lambda as given, multiplied by capital D, divided by a. So watch out for millimeters, 0.12 10 to the minus 3. And in this case, we've got 8 times 10 to the minus 3, which sounds about right. So we'd expect it to be a fairly small gap. So this is 8 millimeters, which seems about right. Part B is a little bit more complex, possibly. Sketch the variation of light as it varies from the midpoint. So we know that we're going to get high intensity, bright light in the middle, and then a dark patch, and then we're going to get another bright patch, and then a dark patch, and it should be symmetrical about both sides. So what's important to note here is it's not a binary thing. So it's not bright and then dark and then bright, even though in simplistic terms that's how we describe it. Because in the midpoint, where we have these two waves meeting in phase, then we get our maximum amplitude constructive interference. And at the first dark fringe on the left and on the right, then the waves effectively cancel each other out. But between those 2 points, we have a gradual change from both in phase, in the midpoint, to both out of phase or antiphase at the first dark fringe. So there's a gradual change. So this is actually a sinusoidal relationship. So we go from maximum, gradually down to minimum, back up to maximum, back down to minimum, and it's symmetrical about the midpoint. We could also talk about, well, why is there a reduction here? Why is it not just the same amplitude repeated throughout, the same as the midpoint? The reason why is because the waves, both waves have traveled a little bit further, then their intensity has reduced slightly. The waves have spread out a little bit more. So when they do meet in phase, the original waves are slightly less intense than they were when they traveled less distance, so we get a slight reduction in amplitude. So this is why the central fringe is the brightest, and then it's slightly less bright on either side, and then less bright again, and eventually it approaches zero brightness. Right, question 2. So part A is fairly standard. We saw something very similar to this in the previous video. So it's always useful to make reference to the formula. So if we just describe it, we may not get full marks. So it's good practice to say according to the formula with y as the subject. So y is the fringe separation is equal to lambda d over a. So if we decrease the slit separation, so a is the slit separation. If you make that smaller, then in order for this to still balance, then y will be larger. So if you divide by a smaller number on the bottom of the fraction, then we get a larger value on the left-hand side. And the benefit of this is it increases the fringe separation. That's a useful thing. It's easier to measure if those bright spots are further apart. And as we said, it reduces the percentage uncertainty. So your uncertainty is fixed. That will be with the ruler. That might be plus or minus a millimeter. But because the distance you're measuring is greater, then the percentage uncertainty will be smaller, which is a benefit. Why the minimum intensity is not 0? Well, this is quite a difficult question. And in fact, on the previous question, we were kind of assuming that this did go down to 0. But in actual fact, it's not quite 0. So we did say that where they effectively cancel out, the path difference will be 0.5 of lambda or 1.5 or 2.5, so we've got this n plus 0.5 lambda. So you would expect them to cancel out. However, one of those waves has had to travel slightly further than the other one. So for the same reason we said in the previous question, that when they meet in phase, then the combined intensity is going to be slightly less. The same applies to when they meet out of phase. So one of those waves has had to travel slightly further. So the intensity of those two waves meeting at the dark fringe point, one of them will not be quite the same intensity as the other. So they almost cancel out, but they're not actually the same amplitude because one has had to travel further and therefore is more spread out. So we might, in simplistic terms, say that it's completely dark. However, that's not strictly true because one wave has had to travel slightly further. So that distinction there is probably A star. It's quite a subtle point, and it's a good one to note for exam questions. Okay, question 3. So this is a fairly standard question, certainly part A. So we're told the diffraction grating is 1,000 lines per millimeter. Sounds about right. We're looking at helium gas, so this is spectroscopy. This is used to analyze different types of elements. For example, if you're looking at light from a distant star, but in this case it's just helium. And we're told the first order maximum, so this is n is equal to 1. So it's the first dot on either the left or the right hand side. And we haven't just got one because we've got several different colours. We've got 3 colours in this case. So this is different to monochromatic light. Monochromatic would just be, for example, red laser light of a particular wavelength. So this is a little bit more difficult. So theta 1 for one of the colours is 26.6. Theta 1 for another colour is 30.1. And theta 1 for another colour is 36. Okay, so all we need to do here is, well, the first thing, as always, is to calculate the value of D, which is the slit separation. So D is equal to 1 over the number of lines per millimeter, but we need to convert this into meters. So if I have 1,000 lines per millimeter, then if I change that into how many lines per meter, in a meter, well, that's 1,000 times bigger. So I have 1,000 multiplied by 1,000. I have 1,000,000 lines per meter. So D is equal to 1 over 1,000,000, which gives me 1 times 10 to the minus 6 meters. So the separation between the slits, D, is 1 10 to the minus 6. It's a very, very small value. Once we have D, then we should be able to calculate the lambda for each of these 3 thetas. So make lambda's the subject already. In this case, D sine theta over n. So we've got D, 1 10 to the minus 6, multiplied by sine of 26.6, divided by n equals 1. So this often causes confusion. People think, well, what is the order? Which one are we talking about? All it really means is if n is 1, it's the first dot on the left or the right hand side. If n is 2, it's the second dot on either side. If n is 3, it's the third dot, and so on. So we can put the numbers in, and we get 4.48 times 10 to the minus 7, or 448 nanometers, which sounds about right. That's going to be visible light, which would suggest it's correct. So this is why it's useful to remember or to know that the range of visible light is from 400 nanometers to 700 nanometers. So if you get a value outside of that, and we're talking about colours that you can see, then you've probably made a mistake. So we can do the same calculation, but rather than 26.6, we use 30.1, and then again 36. So we have 3 different wavelengths, all of visible light, of the 3 different colours which are present in this spectrum. Part B is a little bit more difficult. I would say this is A star. Calculate how many orders would be observed for each of the 3 colours. What that means is how many lines or dots of each colour would you see on either side. So remember, the one in the middle is the 0th order, n equals 0. So how many orders? Well, that's 0, so you'd have 1, 2, 3 on either side, if that's what we're referring to, if we have n equals 3. So what we need to do is to find the value of n. So rearrange this formula to make n the subject, n equals d sine theta over lambda. So we need to, for our first lambda, this is our 4.48 10 to the minus 7, and we're trying to calculate how many dots basically. So d is the same, And we use sine theta when theta is equal to 90 because we have a screen and the laser light can be deflected. If it's in the middle, then it's 0, and then that will increase up to 90 degrees. And we cannot go past 90. If it goes past 90, then it's effectively coming back the way it came, and that wouldn't be visible, and it doesn't happen. So our maximum space to operate in is an angle of theta equals 90. So if we calculate what would the value of n be for theta equals 90, then that will give us, for this first one, what have we got? N equals d over lambda. So as we said here, sine theta is equal to 1. So this simplifies to d over lambda. So the d is the same for each one. The lambda, the wavelength, is what we've calculated up here. And we're going to get a different value for each one. So for the first one, as we can see, we get 2.23. So what does that actually mean? Because you cannot have 0.23 of a dot. So we've got 2 dots. So that's n equals 1, n equals 2. The 0.23 means, well, we're somewhere between 2 and 3, which means all we actually see is 2 orders. So 2 dots on either side, plus the one in the middle, that would be 5 dots. With the second one, we get 1.99, so it's almost 2. At 90 degrees, we're almost getting the second dot, but not quite. It's slightly under that. The only dot we would see on either side is 1 dot, so we get 1 order. And then similarly for this third wavelength, we get 1.7, so that's less than 2, so we only see 1 dot on either side. It's a little bit more difficult, and I would say this is A star. Okay, so question 4. Some specifications you're expected to do this derivation. On others, this would be an extension question, A star. So we've got 2 lines, 2 slits. The separation is d, as we know. The reason they meet in phase is because this one here has to travel slightly further by lambda, by the wavelength, which is why they meet in phase. And remember, this is not just 2 slits, we have hundreds of slits. So if this is theta, then I can do a little bit of geometry and work out that theta here, the angle here, is also theta. So I have a right angle triangle. So sine theta is equal to opposite over hypotenuse, lambda over d. So sine theta 1 equals lambda over d. For the next angle, I'd have a difference of 2 lambda. So sine theta 2 is equal to 2 lambda over d. And then we could continue this. So we get a pattern of n, 1, 2, 3, n lambda is equal to d sine theta.